Hi. Can you hear us?
Hi, 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 hi,
Hi.
hi, 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 hi.
Hello, everyone. We're going to wait for maybe 1 more minute, and then we'll start our class today.
好，我在上课。
Okay, can you all hear me? All right, so hello, everyone. I'm Kevin Chang. I'll be your instructor today, and today we'll be talking about mathematical modeling, and specifically a part of modeling called deterministic modeling. So I'm sure hopefully people will keep joining as we progress with the lecture, but the main point of today's lesson and the seminar will be to introduce all of you to some topics and ideas in mathematics that is not used in competitions, but more of real life careers, jobs, and how mathematics is actually employed in many different aspects of reality. So you can probably imagine that mathematics is not just for your competitions at a middle school and high school level. It's not just to do research. It's not just to discover more about it and write theorems. A lot of mathematics nowadays is used to actually help us in different various fields. We have mathematics used in fields like engineering. Mathematics is used a lot in areas like economics and finance, and in biology. A lot of different areas like these all employ very complicated mathematics to help them. And we'll explore why mathematics is so useful in the real world today. And so I'm going to first start off our lecture today by discussing what a model really is. So our first question is going to be, what is a model? And of course, the definition of a model will vary between different teachers, different people, but in general, it'll mean the same thing. A model is an approximation of what reality is telling us using mathematics and our observations. So by observing different properties and factors and different aspects of reality, we can convert those into mathematical relations and use those mathematics to help us predict, understand, and analyze what is happening in real life. So I'd say that a model would be an approximation, of course. It is a conversion of our observations into math. So by doing this, we can handle real life in a language, a mathematics that we can understand and manipulate. So obviously, models will have different types of models. So if we model one thing, you can have a very simple model, which might be very inaccurate, versus a very complex and very advanced model that can be very, very accurate and precise. But there will be trade-offs between these. So I'm going to draw a spectrum here. I think this is a very important thing to know about models. So for models, we will have a spectrum between very simple and easy models and very complex and hard models. So a simple model will be very easy to produce, very easy to understand, and it'll be inaccurate. It won't be fully detailed like what reality really is, but it'll give us broad facts and intuition. So it might not give us the most accurate prediction of real life, but it'll give us a general idea of what's happening, and that might help us understand what we're dealing with. And on the other hand of our spectrum, we have very complex models. So these models are very difficult to create, but they're often very precise and accurate. And the only problem with very complex models is that they'll require a lot of data and parameters. So the more complex you want something to be, the more input information you'll have to give it. So if we want to model, let's say, a person, we can easily draw a stick figure for a person and say that's a human. But that's a very simple thing. We might understand that they have 2 arms and 2 legs and a head, but we don't get much out of it. However, a very complex drawing of a person, this model, would be very difficult to create, but would be much more accurate. But at the same time, we would need to know a lot more about the human body, how it should look, what kind of a shape of a body we want to draw. And so that's going to be the data we require to create the complex model. And so for these models, I think we have to understand this important quote by Albert Einstein right here. So this is a very interesting quote that he said. He says that as far as the laws of mathematics refer to reality, they are not certain. And as far as they are certain, they do not refer to reality. So what he means by this is that we need to understand as people that mathematics is only a tool that humans have created to understand and interpret reality. Reality is not defined by mathematics. You'll never get an exact result from mathematics that applies to reality. It's certainly just a tool that will help us understand. So whenever we use math, whenever we make calculations and we try to predict things, we have to understand that no matter how well we create this mathematical model, it's never going to be reality because mathematics is only a tool to approximate reality. And so I think that's a very important takeaway from the concept of modeling and just mathematics in general. You can't be doing math and thinking that by doing math, you are completely understanding the basics of our world. That's just not true. We are simply understanding a way to interpret the world. And so I'm going to talk a bit about, what modeling can be used for. So we haven't talked about any math yet, but I'll talk about some uses for modeling. A very relevant example for today is going to be modeling diseases. So so we have diseases as one of them. And for example, right now we are under the COVID-19 pandemic, and for governments and different officials and authorities across the world, they need to make decisions to minimize the damage that these epidemics and diseases do to their people. So when we ever make policies and stuff, we need to have a good contextual understanding of what is happening with the disease, like how it can spread, how many people can be infected, what kind of people are the most vulnerable to these diseases. And this kind of information can't always be gathered based off pure observational data. Instead, this is going to require a lot of mathematics behind the scenes. We have a lot of mathematicians in the US, in Europe, in Asia. They're all working on modeling COVID-19 and how it spreads, what kind of numbers we can get after a certain period of time. And with this information, we can give this to government officials so that they can decide on what action to take. So proper modeling should be able to provide us with predictions. And remember, predictions aren't always going to be 100% true, but they're going to be better than random guesses. So you wouldn't want your government to be randomly guessing what a disease is going to do. You want them to have a decently accurate prediction that at least has mathematical and logical backing behind it. So that's one example of modeling. Another one we can talk about is going to be under biology and ecology. So for example, we have a lot of parks, we have a lot of different forests and areas around the United States. And these ecosystems have all been around this area for much longer than we humans have. But because of the way humans are, we often damage the environment around us, and this can have tremendous impacts on animals and different species living in these forests and different ecosystems. So by modeling ecology, we can model how species will grow, how they'll shrink, and using this information, we can understand how we can approach preserving the natural wildlife in America. So these are all examples of modeling. There are definitely a lot more that I'll talk about later and in next week's lecture. But for now, we'll talk about just these two. And one more thing I'm going to talk about is what does it mean to be deterministic? So today's lecture, Deterministic, is about deterministic models. So the term deterministic means that we are modeling and we are creating determined results. So no matter how many times you compute the results of the model, it'll give you the same number. It'll be a definite certain number that'll come out of it. So it's not going to be dealing with probabilities or random chances. It's going to be a determined number. So that's where it comes from. It comes from the word determined. I'm sure there's a Greek root for it that they both share, but essentially it means that we are determining exactly what is going to happen. Of course, it's not going to be exactly with reality, but it's going to be exactly in our model. So I'm going to give us a simple example, and we're going to understand how we can produce models from real world problems. So in this case, our example here is going to be, we have a population of a single species, and this species occupies a closed area with a limited quantity of natural resources. And we want to model the size of the population with time. So if you've ever studied biology, you've probably heard of this problem before. But if you haven't studied biology, which I actually haven't at your age, this is going to be a very interesting problem for us to approach. And the result we get in biology comes from the math, actually. So let's see how we're going to do this. So we have a single population, let's say a population of size p. So obviously p is going to change with time. So time t. So these are going to be two of our variables here. So we're going to have the population, we're going to have animals inside a certain area, and they're all going to be the same species using the same resources. So instead of analyzing all of the animals in this area, let's focus on one specific individual. So individual. So let's say this individual's name is Bob. So he might be a deer or some other animal. So we have Bob here, and he's going to be living inside this area. And we have to think of what kind of factors could potentially increase his chance of survival. And remember, surviving as an animal means you're able to reproduce and increase the size of your population. And what other factors could decrease Bob's chance of survival, meaning that he would die, and that'll decrease the size of our population. So for Bob, factors that will help him are one obvious factor is less competitors. Obviously, the more of that species that Bob is in occupies a single area, they're all going to be competing for the same resources. So the less p there is, and the less number of this population there are, the better it's going to be for Bob, because he won't have to compete with all those other individuals for the same resources. So less p is going to be good for him. What's going to be bad for him is obviously the opposite. The more the more animals there are, the worse off Bob will be. And obviously Bob himself, if he survives, right, he's going to have a constant reproduction rate. So constant reproduction, right? Every individual is only going to reproduce about an average number of times. It's not going to have a higher number of reproduction just because there are more people out there. That's not how animals will interact. So from this, we can conclude that Bob's chance of survival increases with less p and decreases with more p. So let's think of a kind of mathematical relation that can sum this. So here I'm going to use some number, let's say a constant, minus p. So let's look at this expression right here. Why does this sum up these factors right here? So for Bob's chance of survival, remember, with less p, less population, a smaller value of p, this factor is going to be larger because it's constant minus p. However, the more population there is, this is going to be a smaller value, meaning that Bob's chance of survival will be lower. So this is a good factor that we can consider. This makes sense. And now this would be Bob's chance of survival. At the same time, we're not going to, let's not look at just Bob anymore. Let's look at the entire population. So the entire population is basically consisting of a whole bunch of individuals just like Bob, and they're all going to share this same kind of factor, right? The more other competitors they have, the lower chance they have of living. And so because there are going to be P individuals at one time, we're going to multiply this factor by a factor of P for the rate of P's growth. And this should be a proportionality here. So this is going to be our mathematical expression. So P is going to be increasing at a rate proportional to both the size of P, because that's how many individuals we'll have, and each individual will be increasing the number of the population by reproduction based on how well they can survive. So essentially, this is what we're doing here. And there are many ways to interpret this. We can also interpret this via individual proportionalities. You can say the rate is proportional to P. It's also proportional to this. And that's another way of interpreting this. However, this is the general relation we will have. Oh, and if you have any questions, feel free to ask either me or your TA, which is Brian in this class. So shoot us questions. I'll keep an eye on the chat, and Brian will answer your questions if you have any as well. And so essentially what we're doing here is we have a rate being proportional to the size of the population multiplied by this expression right here, a constant minus P. And this is great and all, but how can we analyze mathematically this relation? Well, we're going to need to handle rates here. So remember, this is the rate of P's growth, the rate of the size P changing versus time. So to handle these kind of equations, we're going to need to introduce a topic, which is the derivative. So if you were present for the calculus seminar, we already talked about derivatives there, but I will give a brief rundown over here. And a difference I should stress is that when we are handling just pure calculus, often we want to evaluate derivatives or integrals. But in this case, with modeling, mathematicians have a tool at their hands known as the computer. And computers are very, very powerful at calculations. They might suck at ordinary math problems and they can't actually solve these kind of logical thinking, but they're great at computation. So mathematicians who are modeling can often manipulate calculus equations and different things to become computational based, and they can feed that into a computer and have the computer calculate the results for them. So in this case, we're not going to be focusing on all the different calculus rules, all the different properties. We're going to focus on the definition of a derivative, and then we're going to talk about how we can implement that into a computer to solve these kind of equations. So first, I'm going to briefly introduce what a derivative is. So imagine we have a function f of x. So I'm going to draw a random curve here. Let's say this is f of x. So f of x, x. So in this case, the derivative at any specific point, for example here, this derivative is going to be equivalent to the slope of the tangent line, meaning if we were to zoom in infinitely closely into that curve right there, so maybe something like this, if we were to zoom infinitely in, it would become very close to a straight line. And we're going to find the slope at that straight line. So essentially what the derivative is it is an instantaneous slope. So you'll see these terms used a lot, instantaneous slope. It is a slope at an exact point for a curve. So instead of a slope between 2 points, it is a slope at the exact point. And we can define this using a limit. So a limit is essentially we're saying a specific value is approaching some sort of number, and we're going to evaluate that. So in this case, let's look at this curve again. We have this curve, and we take 2 random points on it, and we draw a line between them. You'll see that this line is probably pretty close to the instantaneous slope of, let's say, a point in between. So if we were to squeeze these points infinitely close to that one point, the slope between these 2 points would be our derivative. So essentially, that's what our derivative definition is here. We are taking the limit of this small difference. The small difference is going to be the difference between these 2 points, delta x. As it approaches 0, we're going to look for the slope between these 2 values right here. So you can see we have f of x plus delta x. That is going to be the value of f of x here, minus f of x, which is the point here. So x is going to be x plus delta x. And the slope between these 2 points, as the difference between them approaches 0, is going to be our derivative. So this is the formal definition of a derivative that you'll see in classes like Calculus 1. So over here, with the differential derivative, we can now approach a couple more topics on how we can manipulate derivatives. So I'm going to talk about a property known as discrete points. So I apologize if we are moving through this material really quickly. We have a lot of things to cover, and I hope I can cover everything because it's quite interesting. And I have a handout prepared that I will hopefully release sometime soon. I am a bit busy right now, so I cannot promise that I'll release it in the next 2 to 3 days. But okay, let's go back to the lesson. We have discrete points. So what does it mean to be discrete? So in mathematics, the word discrete means that we have separated non-continuous information. So example, a continuous is the opposite of discrete. A continuous curve is something like this. This curve is continuous. Ignore that thing right there. So this is a continuous curve because at no point are we breaking apart. Everything is flowing, it is continuous, it is smooth. So a discrete set of points would be something like this. These points are not connected. They are data, maybe from a curve, but they're not connected and they're certainly not continuous. So that is what it means to be discrete. So why is discrete useful in mathematics? Well, like I mentioned earlier, if we have a derivative, f prime of x, if we have a derivative like this, by the way, if we write y equals f of x, we can write f prime of x as dy over dx. This is just notation that we use in calculus. And if you don't understand much calculus, that's fine. I hope you'll take out some information when you watch these lectures again. And I'll certainly talk about non-calculus things very soon in the future. So when we write this derivative here, we can solve, let's say this is equivalent to some function g of x. We can solve this maybe with hand, with our normal logical assumptions in mathematics and properties of derivatives. But for a computer cannot solve this very easily at all. So instead, we want to feed it different numbers. It's very good with numbers. So if we can break one curve that maybe we're finding a derivative on into many points, a computer is much better at handling those points. So that's why we're interested in discrete points in this case. So I'm going to talk about, let's see. This is good for computation. Good for computation. And let's talk now about something known as the Euler method. So essentially, let's go back to the definition of a derivative. So I'm going to write it again. A derivative is the limit as delta x approaches 0 of f of x plus delta x minus f of x over delta x. And let's say this function f of x is going to be a curve like this. It's a very basic curve. Now, remember, if we are to try to find a very accurate derivative, we want the distance between these 2 points to approach 0, as we describe here with a limit. However, let's say that we don't want a precise derivative. We're okay with slightly off derivative. So in this case, instead of making it approach 0, we'll just say that delta x is very, very small. We pick a very, very small number. So this expression right here means that delta of x is much less than 1. So in this case, let's say we can say delta x is equal to 10 to the power of maybe -9. This is a very small number. And for many functions, many nicer functions, using this in this definition right here, this expression for some function f of x, this will give you a slope between 2 points that is very, very close to what the derivative actually is. And remember, with models, we can have very simple, we can have very complex models, but we don't always need to strive for the very most precise kind of model possible. There will always be an error in our models. So if we can accept a certain amount of error within our calculations, we are okay with using approximations when we are dealing with expressions. So we can write that the derivative f prime of x at some point x is approximately, and approximately because we are using some very small value of delta x, it's going to be approximately f of x plus delta x minus f of x over delta x. And there's no limit this time. This is just a very small number. And this is important because for our curve here, let's say that we, instead of having a function for the curve, we have a set of data. So for example, like this. And the distance between each of these points, let's say, is delta x. Well, in that case, instead of finding the derivative using hand, like our hand calculations, we can just use a computer or a calculator to compute the slopes between these points with this very small delta x. And so in this case, we took a curve and we made it discrete. We discretized it. Discretizing means we broke it into separate individual points that are not connected. And we use these points, which have numbers, values of f of x attached to each of them. And we can use those to compute approximate derivatives. So this is going to be an approximate derivative. And now let's rearrange this. Let's multiply all the sides by delta x, and we can have the expression f of x plus delta x is going to be equal to f of x plus f prime of x times delta x. And this is not an equal. This should be an approximate. So this is actually even more interesting. Before we were just talking about calculating derivatives given these points, but now we can say that, let's say we were given this point right here, and we are told what its derivative is. We are told that maybe f prime of x is equal to some constant c at this point. And now we can calculate the next point. So if this is, let's say, this is at point A, this is at point A plus delta x, we can calculate what f of A plus delta x is using the value of f of A and whatever f prime of A was at that point, so equal to c. We can use this expression right here, this approximate, to approximate what this value right here will be. So this is a method known as the Euler method, and that's the name of my page right here. So this is the Euler method. Essentially, if we are given a derivative, we are given, and we pick a certain delta x, and we have an existing point, we can predict the next point using this expression. And so it's not going to be super accurate, and it's going to depend on what kind of function we're handling with. But in general, I'll cover this as the basic knowledge you'll need for today's lecture. So for our example here, given that f prime of x is equal to 2 times x for all x, and that f of 0 is equal to 1, we will use theorem 2.2. This is theorem 2.2. This is from our handout, by the way. So theorem 2.2 to estimate f of n. So we can imagine ourselves with a point x equals 0, and then f of 0 equals 1. We are given this information, and now we can use this to try to find f of n. So the first thing we need to pick is we should pick what our delta x should be. So in this case, we want our eventual x value to go from the 0 all the way to the value of n. So remember, each time we are incrementing by delta x. So let's just say that delta x is equal to a number n divided by some number, let's say k. So the k is going to be an integer here. And we're basically splitting our domain, which is from 0 to n, into these k individual parts with delta x, which is the interval between them, of n over k. Okay, hopefully you guys don't have too many questions. Okay, looks good. So now we can first start. We can go f of x. So f of 0 plus delta x is going to be equal to, let's plug that in from our Euler method here. It's going to be equal to f of 0 plus f prime of 0 times delta x. So f prime of 0, remember, f prime of x is equal to 2x, so f prime of 0 is equal to 0. And this is going to be equal to 1 plus 0 times delta x is equal to 1. Now, if we do this again, f of, now it's going to be delta x plus delta x is equal to f of delta x plus f prime of, and this is going to be delta x this time times delta x. And this is going to be equal to, remember, f of delta x right here is equal to 1, plus this is going to be equal to 2 delta x times delta x. And this will simplify to 1 plus 2 delta x squared. And now if we keep repeating this process over and over again, so like this, equals, and I'm just going to directly substitute this value now, 1 plus 2 delta x squared plus f prime of 2 delta x. When we plug in this, it's going to be 4 delta x this time, this value. So we should get that this should become 1 plus and then 6 delta x squared. And now if you're familiar with recursion, or you just notice a pattern here from repeatedly calculating more values of f times some delta x, f of some number times delta x, you should notice that by the time we get to f of n times delta x, this should result in the expression 1 plus, it should be n minus 1 times n delta x squared. Hopefully this is correct. So you can notice this by just repeatedly plugging this in and using some simple summation tricks, or just noticing the pattern develop. And so this is how we can calculate, or we can approximate, remember this is an approximate value of f of n delta x, or not n, my bad, this should be a k, f of k delta x. And remember, k delta x, from our definition of delta of x, is going to be equal to n. So f of n is going to be equal to, and then this expression right here. And this should be k, not n. So this is not too complicated of an example. If you didn't understand it, that is okay. I went over this in a lot of detail in the handout, so you can reread that as many times as you want once I post that. And essentially what we did in this problem is we took existing numbers that we knew here and we put them into Euler Method to compute the next set of values and approximate them until we got f of n. So let's move on. We don't have too much time, but I'm going to talk quickly about this concept known as linearization. So linearization, essentially, we don't always have an example. In this previous case, we had f(n) of x is equal to 2x. These are all pretty linear terms. If we convert this to our expression from before, using Euler Method, we have that f of x plus delta x is going to be equal to f of x plus, and then f prime of x, which is 2x. So 2x times delta x. So remember, delta x is a constant that we have picked, something a lot smaller than 1. And then in this case, these are all essentially variables. These are unknowns that we are evaluating for in the recursive sequence. And everything here is linear. We have a linear term here, a linear term here. You can think of these as variables, and a linear term here with x. So in fact, we can move this a further step, actually. So in some cases, this will not be linear, and you'll have to make approximations to convert them to become linear. And why do you want them to be linear? Well, that's because we can express this in a very interesting way. So let's say that f of, remember, let's write everything in terms of delta x. So f of k delta x, let's say this is equal to some number a of k. So a of k is going to be a sequence here. This is a sequence. This symbol, double less than 1, this means much less than 1. So much less than 1. So it's a very, very small number, something maybe like 10 to the minus 9 or 10 to the minus 6. These are all very small. So that's what it means. So essentially, we're making a sequence here with a of k. And remember, using the Euler method previously, we had something like a of 1 equals a of 0 plus, and then 2 times 0 times delta x. A2 equals a1 plus 2 times, and then this one was, should be 2 times 0 delta x. So 2 times delta x times delta x. So this is just from our previous example here. I don't know if I can pull it up onto this page, but it was from this example. So we're just taking those numbers and we're going to look at it through a sequence perspective. So in terms of a sequence, we have something like this. A3 is equal to A2 plus 2 times 2 delta x, and so on until we have AK equals AK minus 1 plus 2 times K minus 1 delta X. So if you notice, this is very interesting because this is a systems of equations. And it's not just any system of equations, it's a system of linear equations. And that's essentially why linearizing our equations are so important. Because, hey, if you know anything about matrices, we can express any system of linear equations as a matrix equation with some number of constants here. So let's say this is expression B. This is matrix B multiplied by some vector of variables. In this case, that would be our sequence from A1 all the way to AK. And then this can be equal to some constants determined by our expressions here. And let's say that is a matrix, it's a vector C. So this is vector A. So if you know anything about matrices, this is a bit complicated, but if you know anything about matrices, we can find all of the values inside the vector A by taking the inverse of B. So this is going to be B to the minus 1 times vector C. So a computer is very good at doing matrix multiplication and these kind of things, like inverting matrices and so on. So all we have to do is, instead of calculating this by hand for a computer, we can translate the system of equations into matrices for the computer, and the computer can invert the matrices and do some quick computation and instantly compute every single value of A1. And remember, of AK, and remember, some number AI is equal to F of I of delta X. So instantly we can compute the values in our function. So that's the general gist of how a computer can do these system equations and solve for different values in a function very quickly with calculus. And I'm probably going to skip this, but essentially we're just talking about differential equations real quick. So differential equations, they're not only limited to the ones that I showed you. There are a lot of them, and a lot of them are very hard to create your own methods and algorithms like I showed you before to do. So there are a lot of built-in algorithms that people and famous mathematicians have already discovered for solving these with computers. So there are some very famous ones. If you're interested, you can search up very good ones such as the Runge-Kutta solutions. So this is N. If you're interested, search this up. There are a lot of famous ones. I personally code in a language known as MATLAB, and MATLAB has a whole bunch of built-in ODE solvers like ODE 4.5. This is a very famous algorithm as well. So all of these are built-in methods in which a computer can solve a differential equation. And so I guess what we should take away from me going over these techniques that we use to solve differential equations is that humans are capable oftentimes of solving simple differential equations, but when we get to very complicated ones, things that are more complex for complex models, in those cases, humans are completely unable to really compute values for these functions. And we need to rely on computers, and some algorithms are developed, including the ones I showed you with linearization. And these algorithms allow us to find different values on a function based on derivatives. And that's essentially what we're doing. We are solving differential equations, so DEs. And I apologize for rushing this really quickly, but there's a lot of information, and I went in a lot more detail with the handout. It's currently like 10 pages long, so you have a lot to read. Let's talk about examples now, though. We're running a bit short on time. So I'm going to talk about single populations. This is the problem we posed in the very beginning. So we have a single population in a closed area. We're going to model it with time. So if you remember from our beginning, we had the relation rate of P with time. The population P, that's the size of the population, is going to be proportional to P times some constant minus P. And now that we are familiar with derivatives are essentially a slope. Remember, they are a rate of change. So the rate of the change of P with time is just the derivative of P with respect to time. And this we now know is proportional to P times some constant here. So some constant minus P. And if we use constants, I'm going to use values A and K. So dP of dt, we can write is equal to, let's say, some number A times P times 1 minus p over k. So I did do a bit of manipulation here. I essentially pulled out this constant. This constant what used to be k, and we pulled k out of this parentheses over here by dividing it with k, and we combined it with whatever proportionality constant we would have to create a. And so this is essentially what this equation means. And essentially, this equation is known as logistic growth. And it's perfectly solvable using ordinary calculus. But unfortunately, this class is not about solving things by hand. We are going to solve things with a computer. So this is the differential equation with the variable t and the function p. So if we know an initial p-value, let's say p of 0, the size of the population at time 0, so let's say this is equal to some number like small p. And we know these values of a and k, let's say from data, we are able to compute the derivative p prime of t using this function. So this is a known value. We can compute it using our size p. Then we can plug this in using our methods, using algorithms, and we can essentially use a computer to solve it, and you should get a graph that looks something like this. So this is going to be our solution. This is a solution curve. And essentially, over here you see what ordinary exponential growth is. It's something like a to the power of t. But over here, this is what we are experiencing with our differential equation over here, this logistic growth equation. And we get this curve. So what does this mean? We can see that initially, when we start at a very low population size, right here, the population will grow with time. It'll grow pretty rapidly at first, but after a certain point, somewhere around here, the growth starts to die down. It doesn't grow as fast anymore. It's starting to, the population size is starting to curve off, and it's going to start approaching this carrying capacity here. So my choice of variable k was no coincidence. K is known as the carrying capacity. Essentially, that is an upper bound on how large a population can get. So if we have a population of animals living by themselves, and they're sharing the same resources, they can keep growing from a small number. They can grow pretty rapidly, but eventually they will start slowing down their growth until they reach this value k, which is their carrying capacity. And that's the value we see in our differential equation right here. So I'm sure when you actually learn calculus in the future, in a classroom example or maybe in a textbook, they will definitely talk about logistic growth, and they'll actually solve this by hand. This is solvable by hand. But in this case, I just wanted to show you guys how a computer would be able to solve it using the techniques we showed earlier. And that would result in, you can use a computer to plot out this curve. And so this is a very simple model because we are only analyzing one species. This rarely happens in reality. There's not going to be pretty much any situation where it's just going to be one species living on their own. But that doesn't mean it's going to be completely useless as well. We can use this to model humans. So humans are a very unique species because we're not very highly impacted by other species. We'll always have a food source. We won't have any predators. We have high technology. We can live comfortably. So that kind of meets the assumptions that we make for a single species population. So you can see whoever made this curve here, this guy, took some initial data points. They took the size of the human population at the year 2000. That is our 0 point on our time. In the population, they took the value here, 5.5 billion. And they started plotting it with relation to years. And you can see this is just a model. I don't know how true this is going to be, but it's just a model for predicting how humans could eventually grow on our planet. So you can see he estimates that by the year 2500, we have 28 billion people on the surface of the Earth. And so his orange curve here is the natural exponential growth. Obviously, nothing is exponential in real life. There are always limiting factors such as sharing the same natural resources and other things that will limit every species to a specific carrying capacity. So in that case, he estimates the carrying capacity to be 100 billion. And that's going to be the k value in his equation. So this is essentially an example of how single population can be applied. So I don't know how much time we're going to have to talk about multi-species, but we can at least talk a bit about double species. So in this case, we're going to have two species, let's say x1 and x2. So we're going to say that the species x1 is going to be our predator species. And yes, this is going to be our predator. and it's going to be our prey. So the species of x1, let's say the size of x1 is just the number, the variable x1. So they're going to be preying on the species x2, meaning that they eat only x2. And x2, let's say, is going to be some species that relies on natural resources in the area, such as plants and trees. So how are we going to model this? Well, we can approach this very similarly to how we approached our initial single species case. So in this case, the rate of x1 should be proportional to some kind of expression. But let's go back to the very initial kind of story I told. Let's say that there's one guy in here called Bob. So one of the predators' name is Bob. And we're going to analyze what kind of factors promote his growth and what kind of factors will try to promote him to die. So in this case, Bob will like it when there is more prey, so more x2. Higher x2 means Bob has more food. And at the same time, what should not make Bob grow more is the more competition there are. The more predators in his same species, they're going to be competing for the same kind of prey. So what might hurt him are more x1. So in this case, the factor we can see here is something maybe that looks like some number constant plus x2 minus, in this case, this should be a whole bunch of constants. So some constant times x2 and minus some constant times x1. So essentially, the more people in Bob's species, the harder of a time he's going to have finding food, competing, sharing room, and things like that. It's going to decrease his chance of survival. But at the same time, the more prey he has, the more x2 there are, he's going to have a higher chance of survival. So we can say that Bob's chance of survival is going to be proportional. So Bob surviving is going to be proportional to this expression right here. And remember, the species x1 is going to be consisting of a whole bunch of individuals like Bob. So our rate should be proportional to the size of x1 times, and let me say these constants here. So let's say something like a1 plus, let's say minus a2 x1 plus a3 x2. So I just rearrange the order here. And essentially, that's going to be our rate. And remember, our rate is going to be dx1 dt, the derivative of x1 to respect to d. And since this is proportional to the constant, if we had a constant here, we just multiply it into this factor right here. And since these are all constants, we don't really need to worry about this proportionality factor. It's just going to be constants like this. So it's going to be equal to, let's say, this exact expression right here. And it's going to depend on some constants that we only determine from data. So as you can see, with more complicated models like this, we are already requiring a lot more data. We need some numbers like A1, A2, and A3 just for X1. And we do the same thing for X2. I'm not going to do it here for the sake of time, but we should have something like derivative of X2 is going to be equal to X2 times some constant, let's say B1. And then in this case, the more of X2 there are, they're going to be sharing the same resources. So in this case, we're actually going to be subtracting X2 and X1. Because remember, the more predators there are, the harder of a time X2 is going to have survival. So times minus B2 X1 minus B3 X2. And so we're going to have two differential equations here. This one right here and this one right here for X1 and X2. And I didn't mention this earlier, but computers are also very good at solving systems of differential equations. And that's because we have something called linear algebra, which can express these systems in terms of matrices and vectors. And computers are great with those. So let's have faith in our computers. And you can see here, I took some time on my own to actually code in MATLAB. So Python is a very good language as well, Python and MATLAB. I would recommend these languages if you want to dabble in these kinds of computational math things. And I've coded the populations for X1 and X2. So you can see here, I put in some random numbers, and we can see initially a very big spike here. And the species here are oscillating very, very heavily. They start tending towards a constant population size. So by the parameters I put in, nature basically decides these parameters, and it'll determine what kind of stable levels of populations these animals can sustain themselves in. So for example, the prey here, and the predator here, the prey can survive at a constant population of around 400, while the predator survives at something maybe around, I'd say, 50 or 75. So these are the constant values that they're tending to. And you can see here, I plotted the size of x2 versus x1 actually. And we can see that the curve goes something like this, and then start tending towards this very common fixed point right here. And you'll notice I wrote this legend right here, Nullcline. And what a Nullcline is essentially we take this expression and the equation b1 minus b2 x1 minus b2 x2 equals 0 is the Nullcline for x2. And so why is that the Nullcline? That's some complicated multivariable calculus related thing. But essentially it's going to be an equation which when you graph it, as you see here, the intersection of these two Nullclines is actually the fixed point at which the species will tend to. And that's a pretty unique thing. And you might say, this is kind of weird, right? Why are there oscillations in species? Do we see this in real life? Do we see this at all in real life? You know, I don't really notice sudden explosion in like rabbits in my area and they suddenly disappear. This doesn't really happen. But in fact, oscillations in nature happen on a very subtle scale. They can take a long time to occur. But there are actually examples of oscillations that do occur very, very frequently, or not necessarily frequently, but very observationally and clearly in life. And one of the famous ones is, I believe it's called the Lynx Snowshoe cycle. This is a very famous biological phenomenon. It's basically, a lynx is a type of cat, and a snowshoe is a type of rabbit. And they live in northern areas where there's a lot of snow. And the cat will eat the rabbit, and the rabbit will decrease the populations when there are too many cats. And then cats will decrease because there are not enough rabbits. And if you notice, it's like, I believe it's every 10 years or so, their population sizes oscillate pretty heavily. And so this is a pretty cool thing. You can search this up on your own time. It's pretty unique. And we're going to skip multi-species for now. I do mention it in my handout, so feel free to go read that when I release it, hopefully next Monday. And let's talk about diseases real quick. I have maybe 10 minutes or so. I have a bit of a technical error. Okay. So essentially, for diseases, we should have some common goals for modeling diseases. We want to predict, and we want to understand how badly essentially the disease will spread to, what kind of people they'll spread to, and how many people will be infected, how many people could die, how many people could recover, these kind of things. So what we're going to handle here is we're going to handle with things known as states. States are going to be essentially every person in a society is going to belong in a specific state. So the most simple kind of model is going to be something called SIR. SIR stands for susceptible, infected, and recovered. So let's say we have a susceptible state, we have an infected state, and we have a recovered state. And I know that's confusing, but I don't mean a state as in like Texas or like Missouri or Louisiana. It doesn't mean like a political state. I mean like a state as in like kind of like a state of matter, like that kind of state. So let's say if you are a person in the susceptible state, that means you are still currently susceptible to the disease. If you're in the infected state, that means you are currently infected with the disease. And if you are in the recovered state, you have already recovered from the disease. So this is a very simple model. We don't have a death state. We could add that if we want the model to be more complex. In this case, I'll just show a simple susceptible, infected, and recovered system. So if you're susceptible, you have a chance of transferring from the susceptible state to the infected state because you could be infected by the disease. So we have a possibility of transmitting from susceptible to infected. And at the same time, we could transfer from infected to recovered if we successfully recover from the disease. So this is how people can move throughout the three states. And we just want to analyze how exactly you're going to move. So let's call the population of susceptible people S. That's going to mean how many people are susceptible. I is going to be how many people are infected. And R is going to be how many people are recovered. And so we can write some differential equations here. So for example, let's first look at the rate of recovery. So the rate at which people recover from the disease, what should this be proportional to? This should be proportional, obviously, to the number of infected people. The more people who are infected, the more people will be recovering at a certain point in time, right? Because for an individual in the infected state, you have maybe like, let's say 2 weeks until you recover. So it's gonna be a constant rate at which people infected are being recovered. So it's gonna depend on how many people are actually infected at a specific point in time. So let's say we have a constant, I'm gonna put gamma. This is the Greek letter gamma. And it's gonna be our constant of proportionality here for a recovery. And now let's look at susceptible people. People who are susceptible, let's say you're in an individual in a susceptible state. You have maybe a constant chance of being infected by the virus or the bacteria or the disease at a specific point in time. And for on average, this proportionality, like the rate at which one individual is going to be infected, is about a constant rate, depending on how many people are infected and how many people are susceptible. So it should be proportional to susceptible people times the infected people, right? The more susceptible people there are, the more of a chance susceptible people will be becoming infected. And the more infected people there are, the higher chance of transmitting it to someone who is susceptible. So from the individual point of view, if you're an individual, the more infected people there are, the higher of a chance you have. So multiply that by the number of people in this state. That's going to be our relation. So let's pick the letter beta for our constant here. And then obviously for our infected rate, there should be a negative sign here. Because remember, we are decreasing the number of susceptible people when we infect them. And for infected people, it's going to be a combination of people who are becoming infected and people who are recovering. It's going to be equal to beta Si minus gamma I, right? Because people who are becoming infected are this term. People who are leaving the infected and becoming recovered is this term. So let's say that we have these three differential equations. This is a system of differential equations. We can use a computer to compute the values here. So I've done the liberty of a bit of coding, and this is the graph I've produced. So blue here is the susceptible people. I here is infected. Yellow is going to be our recovered, which is for R. And essentially, we have 1,000 people in our population. We have maybe like 1 or 2 people who are initially infected. And that is this red curve here. You can see that infected grows and then it curves down. That's how all infections in history have worked. You know, a lot of people get infected at a point in time, and then they start dropping in number of infections because people are becoming recovered. People are recovering or dying from the disease. So in this case, yellow is a recovery. Not many people have recovered at first, but eventually, with more people infected, they start to recover, and eventually we reach a certain point here. So you can see that the number of people who have not been infected by the disease at all is going to be the number of people in this range right here. People who are susceptible, the initial susceptible people, S of 0, minus the final number of people who have recovered, so R of infinity. So infinity, it's not going to be real infinity in real life. It's going to be like a very large number for how much time has elapsed. So I'm going to point out here that in this case, this is just a plain kind of epidemic where it has gone through a population. Some people have been infected, some people have not, some people have recovered. No one's died in our example because we didn't define a death state. But this might seem pretty severe because in this case, we have maybe around, I'd say like 800, almost 800 people in this scenario who have been infected by the disease. That's almost 80% of the population. That's pretty bad. So obviously governments, people, everyone wants a method to try to prevent and limit how badly an epidemic will spread through a population. And so that's where we come into topics of vaccines. So for vaccines, there are two categories of vaccines. There's one called a leaky vaccine, and there's one called an all or nothing. So I'll explain what these mean. A leaky vaccine essentially means that people who get the vaccine will develop an increased tolerance to the disease. And essentially, they have a lower chance of actually contracting the disease when they are met with it. It gives them a degree of immunity. So it's like called leaky because not everyone who gets a vaccine will be immune. You know, some people will get it. It just decreases the chance at which you will get it. However, an all or nothing vaccine means that once you receive the vaccine, you have become completely immune to the disease. You essentially went through like a very minor version of the disease and you have recovered, you have the antibodies necessary to fight the disease, and you will no longer contract it from infected people. So in real life, all vaccines are between these two categories. They're not going to be perfectly leaky or perfectly all or nothing. They're going to be in between. But for our case, let's analyze all or nothing vaccines, since this is the more common definition of what a vaccine does. It gives you immunity. So in our case, all or nothing changes our initial parameters. So in this case, we have the initial susceptible, infected, and recovered people. So the initial susceptible people will decrease because remember, susceptible people will try to have the vaccine taken, or most of them will. And people who succeed with the vaccine will become fully immune to it. In other words, they'll transfer people into the recovered state. So we'll increase the number of recovered people and decrease the number of initial susceptible people. And infected people, they'll still stay the same. So essentially, if we implement this into our model and we calculate the differential equations, we can see that this is what we get. We get an example where we have no vaccine versus 20% vaccinated. So let's say in this case, we vaccinated 20% of the population, as you can see right here. We drop susceptible by 200, and we increase recovered by 200. And what happens? Well, you can see that, first of all, the infected people, the peak has been significantly flattened. So this is a term we use a lot when we talk about diseases, flattening the curve. What does that actually mean? It means we're flattening the infectious curve by decreasing the total number of people who have been infected. And you can see here that the final S0 minus R infinity, this number is a lot better for the case, the dotted line case, where we have vaccinated people. Dotted line is vaccine, and solid line is no vaccine. So the vaccinated R infinity is right here. The non-vaccinated R infinity is right here. So when we vaccinate 20% of the population, we can see a huge boost in the number of people who were never infected in the disease in the first place. Not only that, the number of people who are infected at a certain point of time are a lot lower. So for example, in let's say at week 10, initially it would be this high. Now it's only like this high. This is a lot less taxing for our hospitals and our workers and everyone. This is a lot better for our economy as well. So that is what flattening the curve means. And you'll notice that in this case, the epidemic has been prolonged. This peak we experience in infections here has been moved and shifted backwards. Is this good or bad? It means that the society is going to take longer to recover from this disease, but at the same time will take less damage. And this is a trade-off that governments and officials will have to take note of when they make decisions. And I'm going to go a little bit over time and talk about what quarantine does. So if you think about it, quarantine is very, very similar to the all or nothing vaccine, right? All or nothing. When you quarantine yourself, essentially what you're doing is you are vaccinating yourself by preventing yourself from getting the disease. You don't necessarily transfer yourself to the recovered state because you didn't actually recover from the disease. You're just preventing yourself from ever getting infected. So in this case, I did some manipulation with the differential equations and decoding. I'm showing you here what happens when we quarantine only 20% of the population. When we quarantine 20% of the population, you can see that we have a lot less people who are recovered. That might seem bad, but remember what we're looking for is we're looking for S of 0 minus R infinity. The difference between the number of people who are susceptible and the people who have been infected over time, this is a very big change. We save this many people from being infected by the disease. Not only that, we flatten the curve, just like we did in the vaccine case. This is a lot less taxing for everyone in hospitals, our first aid workers, what are they called, first responders, everyone like this. These people are under a lot of pressure when we do not quarantine or vaccinate our populations. And so we can help these people by quarantining ourselves, by keeping ourselves safe and not in the susceptible group that can become infected. So by doing this, we're helping society. We're prolonging how long we have to do this for, but at the same time, we can potentially save lives. And I'd like to conclude our lesson here by saying that everyone should stay safe and quarantine ourselves and essentially apply a fake all or nothing vaccine to ourselves. And so a conclusion I can make here is that mathematical modeling, this is not going to be an exact replication of any disease at a given time, but just from these mathematical ideas, by translating real world observations to mathematics, we can easily observe the kinds of decisions we need to make for our societies, the kinds of decisions we make as individuals to help people who are hard at work in our society and in our world. So mathematics is very important in this aspect, that it gives everyone an intuition and a degree of understanding of what to do. And it's not always the most accurate thing, but it is certainly much, much, much better than a blind guess at what we should do as a whole. And so thank you for attending today's lecture. I'll talk more about modeling in next week's lecture with stochastic models. It's a different kind of thing. It'll be less calculus-based, I promise. And it'll cover a lot of interesting topics. So please attend, and thank you for coming to today's lecture. I'll give you guys maybe like half a minute to give me some questions maybe, or ask me for anything, and then I'll close the class. And I do apologize because I'm really busy right now, so I will probably not be able to post the handout until next Monday. So that is the date that I'll release it. And yes, for anyone who's still here, I saw that Brian made a good point. I will talk a bit more about diseases hopefully in the next lesson. There are some stochastic approaches and methods to improve our accuracy. And thank you for attending. I'm going to close our class now.